Okay, let's get started. Our speaker today for the last GAP seminar of the semester is the year. That's true. Is Professor Tjitske Starkenburg. Tjitske is at Northwestern University, where she's now a research faculty member, having previously been a Sierra postdoc there as well. Before that, she was at the Flatiron CCA Institute, and she did her undergraduate and graduate work in Netherlands at Groningen with Scott Rager and Alina Helming, and Amina Helmi. And throughout, she's been one of the world's experts on hierarchical galaxy formation and all things galaxy, really. So please tell us more about this work today. So, Tjitske.
Thank you. Yeah, thank you for coming to listen to me today. I'm very happy to talk to you today a little bit about hierarchical galaxy formation and how we can may be able to trace that in looking at the outer parts of the galaxies and all the information that is stored in there. And one thing that I will be talking about as well is how we can use multi-scale simulations and use the power in different simulation approaches to all learn pieces of this puzzle. So to talk a little bit about galaxy evolution first, if we look at the very large scales of the universe, structure formation happens. Dark matter clumps up, you get these large filaments, the cosmic web structure. Inside of that, filaments come together, halos collapse, start forming. Those attract baryonic matter, galaxies form, stars form, they have feedback, there's a lot of interaction. But there's also, from this large scale structure, there's multiple galaxies that are merging, and the galaxies build up hierarchically. Then, on the other hand, inside of galaxies, we have, of course, the gas accretion, which then cools. There's heating from feedback. There are inflows and outflows. There's a lot of gas physics going on. We have star formation, stellar evolution, the feedback of that with stellar winds and supernova, eventually compact objects. There's all the small-scale physics that is encompasses in these and other processes that involves a lot of chemistry with gas, with dust, radiation, of course. There are supermassive black holes at the center that are feeding and giving large-scale feedback as well as small-scale feedback. There are secondary dynamical effects that take place due to instabilities, for example, through involving disks and bars, forming bulges inside of galaxies. And then on a global scale, what people have been interested in is then you can have a quenching of star formation through some of these effects or a combination of these effects that make the galaxy stop forming any new stars, could make it red and dead, as people have been saying. And so thinking about this, you could separate this into the external effects that form the galaxy and the internal effects that shape its evolution. But these are not exclusively, and they interact with each other. And so one question that interests me is, what kind of tracers can we use to untangle all these physical processes and identify what their importance is in the galaxies that we observe? So can we connect observables to some combination of the dominant physical processes that have led to that observable? And so to show you a few examples of what I think are interesting approaches that connect these internal things to external things is, for example, this this one in which, building on a lot of work in a paper in 2020, Bruce Lara et al. Showed that if you look at the star formation history of the Milky Way through its resolved stars, then there are, with relatively high significance, there are these peaks at certain times. And then if you compare that to what people have inferred about the dynamical history of the Sagittarius dwarf satellite around the Milky Way, those peaks seem to coincide with what people have thought of are the pericenter passages of this satellite. So the dynamical effects of this relatively massive satellite falling into the Milky Way could have had an effect on the star formation efficiency in the Milky Way itself, and to the gas physics in the Milky Way itself. And so there's multiple tracers that we can try to combine to actually learn about the Milky Way's history.
Walk us through this plot. What is what?
So look-back time means that we are currently here. The start of the universe is here. This is the normalized total star formation rate of the Milky Way. I think this is they've done a Bayesian approach, and so the orange line is their kind of maximum likelihood of the star formation history of the Milky Way, and the other lines are additional samples from the posterior.
But like they're taking it, they have a model of stellar populations and distribution of those, Gaia and whatever.
Yeah, so based on Gaia and other surveys, they've modeled stellar populations to a large sample of stars in the Milky Way. It's not complete, of course it's not complete, and there are definitely selection functions that are going to matter. But it's a very large and relatively broad sample. And so modeling those stellar populations, they get approximate stellar ages, which gives you this star formation history.
The error bars, what are those?
I'm not sure. I would have to double check on the error bars. Yes. So this is by no means completely known, but it is an intricate example, or an interesting example of when the Milky Way likely had enhancements of star formation, and especially this peak is relatively significant. And also, it's not a complete answer, because there's many papers that have looked at the dynamical history of the Sagittarius satellite, and they do have different inferences about when the barycenter passages happen. But there is some overlap in roughly around here and roughly at a later time. But the interest I had in this paper is that it tries to combine these two different tracers that actually should be telling the same story and are part of the same story. And that we can use that to try to combine what comes from outside with what happens inside of the galaxy. And another example of that is for the Andromeda galaxy, so our nearest neighbor, M31, and where de Souza and Bell argued that this likely experienced a significant merger about 2 gigayears ago, where this is an artist's impression of what that could look like. And they identified a few tracers that would argue this point. Again, I don't think this is the complete answer, or may not be the full answer. but it is an interesting example where, again, things that are that come from outside are combined with processes that take place inside of the galaxy. And again, this is a burst of star formation around 2 gigayears ago, which come from, again, stellar population modeling, in this case from the FAT survey, I think, which resolved the disk of Andromeda in individual stars. A compact metal-rich satellite, which is M32, a rotating interstellar halo of M31, and a giant stellar stream, which has been known for a long time. And more recent kinematics from DESI seem to agree with this picture of having a rotated stellar halo and the kinematics of the stellar stream and M32.
Where's M32 in the top image?
I think it's this one. Yeah. However, so stellar halos, in both cases, we use information that's in the stellar halo. In the first case, it's the major dwarf galaxy satellite, Sagittarius, which is in the Milky Way stellar halo. In the second example, it's the giant stellar stream and the overall rotation of the interstellar halo. So stellar halos give us information and clues to a galaxy's past evolution. And because they are built up out of accreted lower mass systems, they also give us information about low mass galaxy formation as a whole. The best knowledge we have about dwarf galaxies and dwarf galaxy formation is from satellites in the Milky Way, because those are nearby. Those we can resolve. Additionally, structures in the stellar halo, and such as streams and shells, actually are very sensitive dynamical tracers. So they give us information about the host potential and constraints on what the dark matter halo properties could be. And what we'll get to later is that even substructure within the streams may be able to tell us a little bit about the nature of dark matter. However, there are a number of smaller ongoing surveys to identify either satellites, which is the first two large stellar streams, or stellar halos. But this is really a very faint, low surface brightness discovery space for upcoming surveys, or I should say current and upcoming surveys for Euclid, Rubin, and Roman. And so this image shows the PANDA survey of Andromeda galaxy, where the giant stellar stream is very easily identifiable. And the PANDA survey resolved a large part of the stellar halo of Andromeda in individual stars to a limiting depth, and was a giant campaign. Sorry. No, it's CFHT. So the colors are metallicities.
Oh, okay.
Of individual stars.
So is that done with narrowband imaging?
It's narrowband imaging over multiple years.
Okay.
Yeah, so this is a giant survey, basically. And the Roman Space Telescope will be able to do this in like a few pointings. So that's why I say this really is a discovery space for the next generation of telescopes. The challenge is that stellar halos are very faint, but extended. So you need to have deep surveys, but you also need to have a large field of view. And that's very hard to combine. And so there have been some small approaches. and especially for sets of nearby galaxies. And I think this is one of the deepest ones, where they go to a surface brightness of around 30, and they focused on the region around this galaxy using the Large Binocular Telescope. And with this, I just wanted to highlight, so I think the colored images are SDSS, and then all the grayscale is from the light survey. And so you can see some of the difference with SDSS. You would only get the galaxy itself, or this galaxy itself, basically this region. And then if you go deeper and deeper and deeper, you start to resolve all of this extended structure that also connects the nearby galaxies together. And so we can start to see a little bit how these interact.
So is there anything in particular? I don't know. Is it working? Was it working? Okay.
There's a light now.
So this is done with the binocular telescope, right? So is there any reason that, what is the observational requirements to be able to do this? Do you need to actually have a large field of view? And in addition to that, you need to modify your observations probably to have very short integrations so you can actually discern the background over the brightness of the galaxies? Is there something particularly different that you need to do this? Otherwise, because we have telescopes with large field of view for a while. Yes. So what is different about the world of Trujillo that makes it different than before? That you can see that makes you see now these large halos, extended halos.
It is the LBT has been around for a while. So this is certainly, it has been possible for a while. But it is the combination of needing a large field of view, needing many short exposures, but over a total long time to reach the depth, but not be background limited and be able to distinguish the light from your background. And then I think it all comes down to priority and doing this for a larger field of view. But this is an integrated light. And this is similar to what Rubin will be getting us, but then for many, many more galaxies, basically for free, going after Rubin's main goals. In resolved stars, so if we go back, this is like a multi-year project. So this is very hard to do from the ground. To do resolved stars, to have your resolution be able to get to resolution and sensitivity, to be able to resolve individual stars out to distances of megaparsecs, but then also have this field of view. And so Rubin is a discovery space that almost comes for free. Roman is a discovery space that we have a very hard time to get from the ground. Does that answer your question?
Sure. Yeah.
Okay. Thanks. And so in the case of Rubin, and this is a mock Rubin image from simulations, Rubin will hugely increase the samples mostly, but also Euclid and Roman, because they extend deeper, they have a larger area of the sky, they have a larger field of view, so we can do many more nearby galaxies in resolved stars. And what I wanted to mention additionally is that, so one thing is detecting this faint light. Another thing is actually interpreting it. And so there have been some preparatory work to automatically classify some of these tidal features. It's like this again is synthetic Rubin images based on simulations that are combined with a BSF, with noise. And I show you relatively clean examples of what kind of different features people are looking for. But I think in the combined sense, it's like we will see combinations of these features. They will not all be easily distinguished. The full interpretation of seeing this or seeing this and connecting that to galaxy evolution is a much, much harder problem that we haven't solved. And that really is going to rely on combining the simulation side and studying galaxy evolution in those to having these deep observations and doing a data-driven approach. And so that's where I wanted to talk about a range of theoretical ways of looking at this problem and how to make predictions. And so what I've shown in the previous slide is mostly based on large-scale simulations, so large cosmological simulations that have thousands of, well, tens to 100,000 of galaxies, but that have relatively low resolution. And so you can make predictions for especially the largest galaxies where even these faint outer stellar halos are well sampled. But going smaller than that becomes challenging. And going to resolved individual stars is not something you want to do with those simulations. Then there are cosmological simulations that are zoom-ins, where you focus on one galaxy, you resolve it much, much better. There's additional physics, small-scale physics involved. And in those cases, you can do mock images with resolved individual stars. And for example, this shows a synthetic Gaia image based on the fire simulations. But these exist only for a few example galaxies. So they give you very limited statistics. And so I will be talking about this space. It's like approaches that live here. And the first I wanted to take is go all the way to the other side of the spectrum and talk about dynamical modeling in isolated, in most cases, static galaxy or potential models that are often used to look at models of individual stellar streams. And so what are stellar streams? If you have a dwarf galaxy coming in to the Milky Way, for example, due to gravity, that dwarf galaxy or even a globular cluster will be slowly stretched out. Their dark matter halo will be stripped, and the stars will start to form these tidal tails around it, which then form into a relatively narrow stream of stars, which keeps growing over time. And because these are in the outskirts, the real outskirts of the Milky Way, the dynamical times are large, and they get, in most cases, there's not many disturbances, so they can survive for gigayears. Like, they can, in some cases, they can survive for all of cosmic time. And so they provide a relic, basically, of things that have fallen at earlier times. And we have identified, these have been identified in larger numbers since the start of SDSS, basically, in what's called the field of streams. And now with Gaia and Gaia follow-up, there have been way, way more. And the number is growing pretty fast still. So I think we're now up to about 100 streams, which consist of some dwarf galaxy streams and also many streams that we think are coming from globular clusters that are disrupted. And so one project that we did is to see, well, if once we have the Roman Space Telescope, will we be able to resolve these kind of streams? And especially the thin, low mass globular cluster streams in the Andromeda Galaxy. And so what we did is we took a globular cluster stream that's so we modeled a globular cluster stream similar to an existing Milky Way stellar stream. And we took the pandas, observed M31 stars, modeled the stellar population, and forward modeled what that would look like in Roman.
So the pandas stuff on M31 was still a very small field of view where you got high resolution narrowband imaging. To do the same sort of thing to get metallicities for all of the stars in the Milky Way streams, you really need a very, very wide field of view. But is that something feasible to do? Is there a plan for any kind of like narrowband all-sky mission? Yeah, so could we trace individual streams at some level to particular dwarf galaxies that may have been around the Milky Way?
So people are trying to do that with the data in hand, because any surviving dwarf galaxies and globular clusters do pop out in other surveys. So we know probably most of those, not all of those, because they could be, we keep discovering fainter dwarf galaxies as well. So maybe I should be very careful with my words. But people are trying to connect the observed stellar streams to surviving globular clusters or surviving dwarf galaxies, or see whether their properties are similar and they could originate from similar structures.
But
however, the tricky thing is that a detected stellar stream could only exist of like 5 stars, something like that. So especially on the lower mass side, that becomes very hard. It's also most of them are all metal poor. And distinguishing the exact metallicity between those becomes very challenging. And so also connecting them becomes very hard, because everything's metal poor. So here we just looked at stellar densities. So this is a pandas field, and it has 3 stellar streams in there, 3 artificial stellar streams in there. And I think you can maybe see 1, maybe 2. So there is a stellar stream in there that's exactly the same to the Palomar 5 stellar stream in the Milky Way, if that tells anyone something. And something that's 5 times more massive, and something that's 10 times more massive. And so in this case, you see the 10 times more massive probably. You maybe see the 5 times more massive, but you don't see the PAL 5 itself. If we go to what we see in Roman, this really pops out. And so the Roman telescope will be able, or should be able, to resolve globular cluster streams out to pretty low masses in M31, which gives us a huge increase in the tracers that we have in that we will have in M31. And this is true beyond M31 as well, and we think this is true out to about 3.5 megaparsec. And that volume contains around 200 galaxies. Most of those, however, will be lower masses than M31 in the Milky Way. So, as I alluded to before, these very thin, low-mass globular cluster streams actually exhibit their own substructure, and what has mostly been discussed is they can have gaps. And we think that one way in which these gaps can form is through interactions with dark matter subhalos. So clumps of dark matter that are too low mass to have formed a galaxy, or that have been stripped within the Milky Way halo itself, but still survive. They're very dense, they can interact with streams, and that will create a gap. And so this is observational data. And this is the GD1 stream in the Milky Way, where gaps have been seen. There's additional features that people think could be there. And dark matter subhalos is one way this is being explained. But there are other things that can explain gaps as well. There could be resonances with the Milky Way bar. There could be molecular clouds that interact with streams or give rise to resonances. There's the spiral structure in the Milky Way that changes the potential. So all of those could have an effect as well. So to really use these stellar streams to tell us something about whether this very dense clumps of dark matter exist, we need a larger sample. And ideally, in multiple galaxies, because that gives us different environments. So building off the previous work, we asked, will those thin stellar streams that we will be able to see with Roman, will we actually be able to see gaps with those? And this is work done by Christian Aganse, who's now at Stanford, and was a graduate student working on this while he was at UCSD. And so what he did is, again, modeled a Palomar 5-like stellar stream, and in a M31-like background, adding a Milky Way foreground, and then moving this to different distances to see whether you would still be able to see the stream, still would be able to see the gap. And actually, one thing of note is that the exposure times that we're considering here are they're not that long. They're actually similar to what is being considered for one of the Roman surveys, for the High Latitude Wide Area survey. And so in these two cases, you can tentatively see a gap here visually, but visual inspection is kind of tricky. So what we also did is to use a data-driven approach to detect gaps. And this is done using the code find the gap, which uses the gradient of stellar densities in this field to find the location of the largest drops in all directions. And so in this stream, which in individual stars you can barely see anymore here, but this is to highlight where it actually detects the gap. And so again, we use this detection tool in combination with visual inspection to see, well, what is the distance that you would be able to find such gaps? And what we find is that we will be likely be able to detect gaps using this tool or other tools, or doing very careful data analysis in selecting stream stars and then looking at their distributions out to around 2 megaparsecs. And so that includes M31, so we will be able to find gaps in M31, and it includes a few LMC-sized galaxies as well. With longer exposure times and targeted observations for Roman, we will be able to do this further out. And I think yeah. So we likely will be able to detect gaps in external galaxies in stellar streams. So another thing people have recently been finding in looking at this large set of stellar streams in the Milky Way is that it can be that this direction the stars are moving, the stars in the stream are moving, is actually not along the stream itself. And so that means the direction is changing, and what this has been attributed to is actually the presence of the LMC. And the infall of the LMC and the reaction of the Milky Way itself, the Milky Way halo itself, to the infall of the LMC. The infall of the LMC is big enough that it really changes the shape of the Milky Way potential, which has an effect on these very thin and sensitive tracers of the underlying potential. And so another approach that we took is just to see how do streams evolve during mergers, and if we have a larger sample, what can that tell us about any past mergers? And to get a statistical sample with differences in orbital properties and in a well-resolved simulation and systematically changing the parameters, we used a set of simulations, but each has more than 1,000 streams in them to fully explore this whole space. And I will show you just a few of them, where on the left you see just the dark matter in the main halo, and then there will be a satellite coming in. And on the right, it shows just the streams orbiting within this combined potential. And what you can see is that the streams are not following nice tracks. Some of them are folding double, some of them are splitting up, some of them are like flying out to huge radii, and it basically all becomes a mess.
So wait, on the left is
just dark matter.
That's dark matter, and then on the right is
Yeah, so the only thing you see here is the satellite coming in.
But that's not all stars on the right. That's just the streams.
This is just a subset of the streams, yes. And so we put only streams. We only have a dark matter halo, and we only put the streams in.
Yeah, I see. Okay.
But many, many of them.
And fundamentally, does this stream start, like when you put it in, it's already a stream, or you just throw in a globular cluster? And
So it's already a stream, but we do model them at certain ages.
Yeah.
So we explore that from something that's like just starting to form a stream to something that's already pretty large.
But fundamentally, to make a stream, I just take a ball of stars and throw it in, and it's going to... Or is there something else?
You can argue about that. That's how it's mostly done.
Uh-huh.
If you talk to, but actually, if you really want to model how a globular cluster dissolves and forms into a stream, that's actually a field that hasn't been explored that much, and is very challenging because that means that you have to model both the internal structure of the globular cluster and the internal evolution, as well as the external changing external tidal field.
Mm-hmm.
And those ranges have been very hard to combine.
Yeah. Okay.
And we're starting on a project to do that in more detail.
So looking at the animation closely, sort of for 1 gigayear, the individual streams don't seem to be terribly disrupted. But the further you go in time, of course, they go completely chaotic. Is that a way to actually date when a merger occurred? Is dispersion within a stream a useful proxy for how long ago infall happened?
Possibly, yes. And the reason that you don't see much happening within the first gigayear is also because the satellite still has to come in. So the largest effects will be when it really is colliding. But it's like the dispersion, it's like you see them in some streams, but there are actually other streams that are relatively nicely behaved. And so to show you like something of all the streams, so on the left is the initial conditions, and here they're separated out into the inner part of the halo within 50 kpc, and the outer part of the halo, which is at the bottom. And like a very rough trend that we see is that in the inner parts, mostly the streams become much more dispersed, and some get completely destroyed. While on the outer part, it's actually much more that the streams move around. They get more dispersed, but not that much. But they, for example, move out to larger radii, or they move to to smaller radii. But there's no simple, unfortunately, there's no simple one-to-one on what the stream property is, what the merger property is, and how that combines to the evolution. But we do see a large range, and one way to measure how dispersed a stream is to look at the distribution of energies within the stream. And what we do see is between the streams. And so if you look at the distribution of energies of the streams, the change in their total energies, then you see that if a small satellite comes in, there's almost no change, which is this like thin blue line in the middle. And then if you have a larger and larger satellite coming in, you get a very big distribution. But not all the streams change in the same way.
Do these streams have gaps in them? And are there gaps in these streams?
So
Kind of look like they did, but they shouldn't, right? They shouldn't have gaps?
Yeah, they shouldn't. And so the reason that they have gaps is in the modeling, because we first generate the streams to have a certain initial length. And that means that you let the stream grow in the potential, and you have to keep adding particles to the center to keep it growing. But then we have an evolving potential in the merger simulation where we cannot do that. And so that's why it looks like you have a gap forming but that's in the center. Yeah.
So anyway, this is great stuff. So in addition to changing the energy, I suppose it also changes like the angular momentum. Like in this case, it looks like you had a spherical distribution, and so they were moving in planes, and then the streams are no longer coplanar and all of that too, right?
Absolutely. That was my next slide. Thank you. Yeah,
Checks
you're
in the mail.
absolutely right. So another way of looking at this is, again, these are just a subset of streams in initial conditions and now projected on the sky. The middle panel is what these would look like in an isolated halo. So just quietly let them continue what they were doing, and they grow, but they're still on the same track. And then this panel is what they look like in one of the merger cases. And what you can see if you look at some individual colors is that they move. It's like their orbits totally move around. And so that's one thing that changes. It's like the orbital plane of the stream can totally change. The other thing that changes is that if you can fit a parameter space to that orbital plane of the stream where it should be like very nice and narrow, which it is in the isolated case. But then in the merger case, you can see that in this case, this stream is kind of split into two, and there's like all these wiggles happening. And so that could be another signature that there has been a merger, but tracing back to what kind of merger actually, that is something that we have not solved yet. It's like we've been exploring this parameter space and others to try to see what happens to all of these streams, but it's even from these simulations a huge amount of data, and will be a challenge in the coming years to try to really untangle.
Quantify the splitting, folding, change in orbit and so on?
Yes. So changing in the orbital plane and like the dispersion, yes, we can quantify that, of course. And we can look at those distributions. Morphological changes, like streams that split into two, that fold, that's harder to do. Yeah.
Thank you.
I haven't, if you have ideas, I'd be happy to hear. But haven't found a way to really do that yet, except to just look at them. But then ideally, you'd also like to look at the time evolution. OK, so this is actually only filling up this. So how much more time do I have? 15 minutes. 15 minutes? OK. But this is really basically at the opposite end of doing the large cosmological simulations. It's really focusing on one galaxy, on the detailed dynamical evolution within there, with a static or live halo, but at very high resolution. And so what lives in between? And so one thing that we did that's a little bit a step in that direction from doing the high resolution but cosmological simulations is actually to do what they call genetic modifications to the cosmological initial conditions and doing zoom-in simulations combined with flexible empirical models. And so I'll tell you a little bit about what I mean there. So starting from the cosmological, almost Gaussian initial conditions, you can identify a region that is going to form into one galaxy or one halo. And we can follow that, how that happens, how that hierarchical buildup happens for that halo by looking at its dark matter history. And so you could do this in a dark matter only simulation. So one way to then paint on the galaxies in those is to add an empirical model that traces the star formation history and that dark matter history. And then if you want to identify where the stars of all the smaller things that fall into a bigger halo end up, you can do a dynamical tracking, and you can tag stars to dark matter particles and track those through the simulations and see where they end up. And setting it up in this way has its limits. There are certain things that you really cannot do in this way. But the advantage that it gives you, and that we try to explore, is that you can separate out the empirical model and the dynamical model. So you can try to find out what is the dynamics, what is the merger history, and what is the influence of the empirical star formation history. And so on top of that, we looked at the initial conditions of one Milky Way-like host halo and changed it in small ways. That means that you do change the formation history of that halo. And you change when mergers happen. You change how big they are. On top of that, we explored variations in the empirical model. And so tuning, or not tuning, playing with both of these knobs individually can give you a sense of what the effect is of the baryonic physics and what the effect is of the accretion history, the formation history of that galaxy. And so what we showed is that it's like changing this formation history, this buildup of this galaxy, does change what the stellar halo would look like. And so these are examples where you change a reference halo to have actually smaller mergers over its cosmic time, or to have larger mergers at a later time. And it looks totally different. And to compare this to data from the nearby universe, we looked at this plane of the total stellar mass of a galaxy and how much of that stellar mass would be in a stellar halo, would be outside of a certain radius. And then we can see that changing this knob of when the mergers happen and how big they are actually forms tracks in this space. And those tracks span a huge range. They span the full range of all the observational data that we have so far.
Sorry, what is the y-axis? I don't understand.
The y-axis is the mass, the stellar mass outside of 20 kpc divided by the total stellar mass. So it's everything that's the relative amount that's outside of a central galaxy, basically.
Okay. So go later form, so.
Yeah, so there are two families that we've changed. And so in this case, this would be the reference. Later forming means that more of the mass comes in later. So the time at which you have 50% of your mass build up is at a later time in cosmic history. And so in this case, the purples would mean that most of the mass is in place at an early time, and you have a relatively quiet formation history after that. The green ones would mean that you build up slowly, and you actually have a few big mergers at a later time. And roughly the same direction is going from here out to the pink one over there.
Intuitively, help me with my intuition. I would think that things would move over time down because things are settling in and more stuff is settling down.
Yeah, so later forming means that you have bigger things coming in later, so they have less time to settle down.
Okay.
So there's more stars in the outer parts if you have later mergers.
Yes, because it hasn't settled down yet.
Yes.
Okay.
But that's not, and that's the picture that we had in mind as well. But it's not the full story, because here there's actually a turnover.
Yeah. Okay.
And this kind of already goes into the details. The most important thing that we found is that we found a spread. One reason that we think we saw this turnover is because you still have the same total mass at the end. And so the mass that you have available and mergers at different times, they have to normalize. And that is one reason why how much comes in when could have this kink, that there is like a sweet spot where you have your mass formed relatively early, but also in massive mergers, which bring more mass to the center, as opposed to only having minor mergers, which dump most of their stars in the outer parts. 3 minutes? Okay. And so that's one thing that we looked at, but like turning this other knob of the star formation history allowed us to, for example, look at the stellar mass-halo mass relations for dwarf galaxies, which is very poorly constrained. We don't know the halo masses of dwarf galaxies very well, so we don't know how much stellar mass versus dark matter we expect there. And so what we did is compare a number of constraints from the literature, and what you see is that the stellar halo mass, so the mass in the outskirts of the galaxy, changes in a characteristic way if you change the slope. So if you change how much stellar mass per halo mass there is in falling galaxies. But also the spread of these points, of these families, changes as well. And so to us, that was interesting because that means that if you observe more stellar halos and you have a sense of you can measure their stellar masses, you have a sense of how much of the mass for many galaxies is in their outer parts, you can start looking at statistics like this spread instead of trying to focus on individual halos. And there is valuable information that constrains galaxy formation physics in having this statistics. Okay, so in my last few minutes, I think I'm going to wrap up exactly, almost. I wanted to talk briefly about something that fits in between here again, and that is doing this in a semi-analytic way. So all of this needs simulations where we have spatial information, where we look at things that fall in, have an existing halo. But ideally, to get really statistical samples that we can compare to the observed samples that LSST will give us, for example, we need to have way, way more than we can simulate in this way. And so I've been working on building a semi-analytic model that can capture some of this dynamics, explore the parameter space, explore the dependencies, and then can then be compared to observations. And so in this case, as input, I've taken a semi-analytic galaxy formation model. So I don't try to do the full galaxy formation. I just try to do the dynamical part and take orbit distributions from cosmological simulations, and then predict what kind of substructure you would get in the stellar halo. Do things that fall in, do they survive? Do they form streams? Do they form shells? Are they completely stripped apart? What's the stellar halo buildup? And so that means that in this case, I've done this for an LMC-sized galaxy, so relatively lower mass than the Milky Way, but not that much lower mass, and still expected to have its own satellites. And you can follow over time how things fall in, survive for some time, then they form streams or shells, then they slowly get disrupted. And so all of these numbers change over time until at the present day, there's a statistical prediction of how much features and how much structure an LMC should have. And from that, you can say that nearby galaxies, LMC-like galaxies, should have tidal features in most cases. And for Euclid, Rubin, and Roman, we can make predictions of like how many you would see for what fraction of galaxies. And so on the y-axis here is the fraction of galaxies from 0 to 1. And then on the bottom is surface brightness in the visual for Euclid, in R for Rubin, and in the H-band for Roman. And I've tried to add some expected limits there. Whether those limits will be reached is, of course, a question mark. And how many tidal features you expect to be able to see at what surface brightness is. These are not completely forward modeled through the full telescope system. So there's still a question mark whether you will be able to see them in all cases. But it is a starting point to be able to look at this in a statistical sense and start to interpret that observational data. And again, because I can play around with the model, I can go to extreme parameters and see how these change the results. So again, this is changing the stellar halo mass relation. So how many stars are there in low mass galaxies? And it completely changes your expectations. So coming back to the first question, can we untangle the external and internal influences in galaxies? I think using stellar halos, we can study some of this, but ideally we want to combine traces from that trace the external parts, so the stellar halos, to the internal evolution of the galaxy, and get a combined picture. And then I can leave you with my takeaways. Thank you.
So